Hello and welcome to my talk of how to scale Postgres. Today we'll talk about automation, tuning, and sharding. My name is Lucas. Now, how I came to think about this topic is I've spent a lot of time with Postgres over the years. I run a product called pganalyze, which does Postgres performance monitoring. I am a member of the Citus data as well as the Azure database for Postgres teams, where we're looking at how to operate Postgres in the cloud, both on a single server and as well as kind of scaling out. And then I also have just a lot of genuine interest in working with kind of Postgres community and making sure that Postgres is a good database for all kinds of workloads, be it small and large. Now, when we think about scaling Postgres, I would say it's kind of a step-by-step process, right? So oftentimes you kind of start small, right? Kind of the first kind of square there, and then it just starts getting bigger, right? And so you start kind of increasing capacity, right? And so oftentimes a lot of folks, I think, will see that they have a small database and then a slightly larger database, and it's at some point it's just a very large database and it's still running on a single node. I think that's a very common situation for many of us. Second of all, I think many of us also, especially in bigger companies, experience the situation where you just have so many services, right? Like it's just like you start with one, and then there's another team, and then you have like three, and then there's yet another team, you have 9, and then just like starts sprawling, right? And you have so many different kind of Postgres servers that it's getting very difficult to get consistency across them. And so that's kind of the first thing I want to talk about is how do we actually handle hundreds of database servers. And so there is, I think, a lot we could say here. I think really the main point I want to make initially is that consistency is key, right? So I think we need to make sure that when we have this many databases, right, when we look at hundreds of servers, that we apply consistently a certain way of how things are configured. We make sure that the servers are not just ad hoc changed, like somebody doesn't just go into a portal and change the value, and then that opens up a security issue or performance problem. Like things need to kind of be done consistently. Now, the best way to do this, and this has been popular for many years now, but I think it's still so important to think about this, is that we treat infrastructure as code, right? So you shouldn't spin up a virtual machine manually. You shouldn't create a database. Really, what you should be doing is you change a file, you commit that file into a repository, and then that change gets rolled out the same way we roll out software. And so that's why I would really say we need to think of Postgres as well in the same sense, right? So we really need to think about a Postgres infrastructure as code. Now, let's take a look at how that works in practice. So Terraform is very popular these days, right? It's a straightforward way to kind of configure a cloud resource usually. So let's take a look how it works. So we'll actually, as an example, we'll try to modify parameters on our Azure service. Let's kind of take a step back here, actually. So we have two kind of Azure database for Postgres servers here, number 1, number 2. And so we'll kind of, try to make a parameter modification here, right? And so usually when I kind of go here, I could, just change the server parameter, right? Pretty straightforward change. I could just, do it directly in a portal. And so for this example, let's say we want to change the vacuum cost delay. So the vacuum cost delay by default is 20 milliseconds. And we want to change that to 2 milliseconds because we heard it's a good change to make. Now I could change it right here, but actually what I'm going to do is I'm going to do this through the CLI using Terraform. So as you can see here, right, I have kind of, a directory locally on my machine. I have an azure.tf file, which kind of defines the Terraform state. Now, in this configuration file, we have the Azure provider that we're kind of referencing, and then we're using a variable called Postgres config to set the auto vacuum cost delay, right? So you can see here kind of in the middle, I have my auto vacuum cost delay set to 20, and I had applied that earlier. Now what I want to do is I want to make that change here too, right? So let me go right here. There we are. All right, so I'm making that change here, and now I'm running Terraform apply, right? So this, I'm already authenticated locally. And now with Terraform apply, I'm essentially telling, Terraform to go call the relevant APIs and apply this configuration change consistently to both servers. And Terraform now kind of gives me a summary, says, yes, these 2 values need to be replaced. We'll kind of apply that. And so the key benefit here is that if I, use, like for example, I can put this in version control. I could, then do a pull request. Somebody could review this change. Somebody could say, well, actually, you shouldn't be changing this to 2. In our experience, this doesn't run well on small servers. So, we should kind of, maybe split up this configuration, make it, 10 for certain servers, 2 for other servers, right? And so that kind of conversation, that kind of, change management is really what's enabled by treating infrastructure as code. And so, whilst this is running, we can, perfect. Now we can switch back. Let's look at the portal again. Let's reload this here. And so now we should actually see a change applied, right? So now if we look again at the parameter list, we can see that the cost delay is now changed to 2, right? And again, that is done consistently. If we had a third server, we could apply it in the exact same way, and there's no risk that somebody does that by accident. All right, let's kind of go back here. So, I think this is a really important building block, right? And so synchronized configuration is one thing. Now, if you find yourself lucky in a situation where, you use the database as a service that runs in the cloud, which you may or may not choose to do, but let's say you do, right? I think there's many benefits you can get from that, right? So access control is taken care of. You could also use Terraform again to kind of manage that. Automated failover, which I think is a key point for automation, is taken care of with the kind of database as a service providers. Read replicas are usually taken care of or right there built in. Backups are built in. And I think the one thing where a lot of providers are still lacking, including Azure, is kind of that connection pooling is usually not built in. Right, so usually connection pooling is something where you need to install pgbouncer yourself, and you kind of need to find your own automation for that. Now, what I want to talk about here, though, is if you run on your own VM, right? So if you don't choose to use database as a service, but you actually choose to do a self-managed VM, that's where it gets tricky. Because a lot of these things are not taken care of, right? And so you quickly end up with a lot of like badly managed kind of virtual machines that are not consistent. And so we could be talking about all of these, but we don't have time for that. However, we will talk about, I think, one really key project that we've actually initiated 2 years ago called PG Auto Failover. Now, PG Auto Failover solves the very specific problem of having automated failover between 2 nodes in Postgres. So let's take a look at that, right? So it's focused on being simple. I think that's really the key point here. And so let's say you have a primary and a secondary, right? Like typical high availability situation. So the primary server is the one you're writing to. The secondary is usually just used, in emergencies, like to switch over, but it's not actually used for reads. And has a second copy of the full data. And then in the PG Auto Failover setup, there's actually a third node called the monitor node. Now the role of the monitor node is to enable safe automated failover in the case of a failure, right? So let's say the primary fails. Now, how would you know that the failure is not a network partition, right? Like it's not like, let's say, secondary and primary can't talk to each other anymore. The secondary would not be able to choose on its own to become primary because maybe there's just a network blip essentially between the two servers, right? And so that's where the monitor comes in, because the monitor can actually make a decision on behalf of kind of the 2 servers, right? And can essentially say, I see both of the servers, or I don't see them. And so the monitor is essentially the one that kind of, makes that decision for failing over. Now, let's take a look at how that actually works. And so for this, I'll kind of switch to my little Raspberry Pi setup here. So we can kind of see here, right, we have data 01, data 02, and the monitor node. And so these are essentially, like just, simple Linux VMs running Ubuntu Linux. I'm right now connected in my CLI to the monitor node over here, right? So this is the one I'm SSH'd into. And so let me go here, right? And so what we can do here now is, well, first of all, this runs Postgres, right? So if we just do regular PSAUX, we can see kind of, regular Postgres is running. Nothing special about this here. And then now I can use the PG Auto CTL CLI. So PG Auto CTL is kind of PG Auto Failover's kind of command line helper. And here what we can do, first of all, let's look at the state. We're, by the way, also running Postgres 14. I always, for demos, I think it's nice to, if we can, use the latest Postgres version because it helps us also test the latest Postgres versions, right? So Raspberry Pi also runs on ARM, so it's kind of a nice way to make sure that, other architectures work as well. And so right now here we can see that kind of, in this setup right now, the data01 is the primary node, the data02 is the secondary node. Right, and that information is cached or kept in the coordinator, in the monitor. So the monitor kind of knows which of the two is which. So the first thing we can do, and this is just, really simple, is we're just gonna do a planned failover. So we're gonna do this, right? So this is pretty straightforward. So we just say we want to fail over, right? So we want to essentially change places, and we'll just execute that, right? And that will kind of now happen automatically, no other action necessary. And this is, let's take an example, right? Like I want to change shared preload libraries. I want to enable auto-explain or pgstat statements. If I, had to restart my node, that usually takes longer than a failover, right? Because you're shutting it down, that needs to write a checkpoint. There's a lot of kind of changes happening there, and you don't really have a guarantee that the the secondary actually would come up again, right? Or the node itself would come up again. So the benefit here is that with using a failover for maintenance operations, you can actually ensure that the node you're failing over to already runs successfully, right? Is already online, is already has things in shared memory, because you're just essentially telling it to promote. So really, something that enables, I think, a lot of maintenance scenarios to be quicker and more reliable. So now here, right, we can see this kind of completed end-to-end. So now if we show our state again, right, we can see data02 is the primary. Now let's actually connect to these nodes. So in order to do that, we can do this command here. All right, and so the important thing to call out here, and this is unique to PG Auto Failover, is PG Auto Failover uses a mechanism in Postgres called kind of the target session attribute setting, and so that is something that happens on the client side. So if you look at this URL here, which is the one we use for connecting, and we can do this right now. Actually, should copy and paste this correctly. And so the key thing you will notice is that in the connection URL, you have both the data01 and the data02 specified. And so that is helpful because now the client makes the decision which one of the two is actually the primary right now, which one of the two is available to be connected to. And for example, if one of the two was not available, we could still connect, right? We could still connect to the one that's online and that's writable. Alternatives to this are often, DNS based, right? In the DNS record, you update the DNS record when the primary changes to a different IP, or maybe using something like an elastic IP. But all these have the problem that they require usually more infrastructure components, right? So it's really hard to implement in a simple environment. And in addition, things like DNS can have caching issues and so on. And so kind of shifting this to the client is something you can do in modern Postgres versions, which is, I think, the right thing to do. Now, we have a table here called test. Right now it's empty, right? So let's insert a timestamp into this. All right, so we got a timestamp insert here. Now, what I want to illustrate, right, is what happens when we have an unplanned failover. So for that, let's check again what our primary is right now, right? So our primary right now is the data02. So one thing we'll do now is there is a events command. All right, the events command just shows you what has happened kind of on the PG Auto failover kind of side of things, right? So it kind of tells you the important actions that have happened, right? So before it kind of showed us the activity of the planned failover. Now what we'll do is we'll do a watch command here, right? So this will just keep refreshing on its own. And so now I'll do the unplanned failover, which is I'll just disconnect one of these two here. All right. And so the important thing to note, by the way, is that this is actually, also pulling the power, right? So this is like using power over Ethernet. And so when I pull the network's cable, I also pull the power. So it's kind of really like a hard crash, right? You will notice that this takes a couple of seconds. So now essentially what happens is that the monitor, tries to confirm if the secondary is, or if the primary is truly down, right? So right now, we're essentially running in a timeout, and we're kind of checking if, something is like no longer available. And we'll give this a few more seconds. Perfect, there we go. So now you can see, right, after about 10 seconds or so, the monitor decided that the data02 node was unavailable, right? It became unhealthy. And so now what we're doing is we're essentially telling the data01 node to become primary. And without having done anything, right? All I did was plug the cable out, and everything else happened automatically. And so this will probably take another moment or two. And so once it has ensured consistency, it will actually bring up data01 again, right? So if I now repeat what I did earlier, which is I try to connect, we can see that I didn't have to change anything in the connection string, right? I still have both hosts specified, and I was able to just connect directly. And even more so, I could do an insert, right? So this is actually writable. Now, what would happen if I plugged in the older one again, right? So if I enable my watch command again here, I'll kind of plug this in again. Let me just fix it here. Now, obviously, this will take a brief moment, right? Because it actually has to boot up a system, kind of Ubuntu in this case again on that Raspberry Pi, and then what it will do is it will connect back to the monitor. It will check what its state is, right? It will realize that it is no longer the primary, and so then it will try to find out where did we kind of depart, right? Where was that divergent point? And then it will potentially do a PG rewind to kind of walk back the timeline a little bit, and then kind of become the secondary, right? So we can see here, after about 5 to 10 seconds, it found out that, it came back up, right? It found out that it was demoted, it was no longer the primary. And then it's kind of, switching into the catching up state to actually, become a secondary again. And so now, if we waited a few more seconds, we would see that kind of, it becomes back. Perfect. Yeah, and now we're actually back to synchronous replication, right? So this is important, is that, whilst all these things are happening, there's a trade-off here between, having always consistent writes to two locations or having availability, right? And so here we choose availability. Like, we're intentionally saying when the secondary is not available or the primary fails, right, and we switch over, then temporarily we only have one copy, right? Because oftentimes that is a better trade-off. Really what you're trying to do is be as available as possible, even though if that means that, you might temporarily not have something like synchronous replication. All right. So with that, let's switch back. And let's talk about tuning. All right, so for tuning, I think, there's a couple of things we could be talking about here. I just want to give you the highlights of what I think is most important to think about when you're tuning. Because oftentimes we scale out because we haven't tuned, right? Because we just, thought it's easier to just add more hardware. When really what we should be doing is tuning Postgres. And so there's a couple of key things I want to talk about here. The first of all, I want to talk about Workman. So Workman is, a setting that by default doesn't have a good value necessary in Postgres. It really is a trade-off between running out of memory versus, having operations spilled to disk. So the default, which is 4 megabytes in Postgres, means that when you have a sorting operation or a hash operation or a group operation that happens as part of query execution, if that exceeds 4 megabytes in memory use, it will spill to disk. It will create temporary files in order to, not use more than the 4 megabytes of memory. And that can be the right choice, right? If you're very memory constrained, that is probably the right choice. However, it does mean that things might seem slower than they could be if you just made more use of your already available memory. And so, this is something that you can look at in detail using two kind of statistic views. You can look at pgstat database, which has a 10 bytes field, and you can look at pgstat statements to get a per statement breakdown of this. And so the other thing you can do is you can turn on logging here. You can set log temp files in Postgres. And then, it will tell you this is the statement that I ran, and this is kind of the temporary file it created. Now, the general, guideline here would be if something sorts and that spills to disk, right? If you get like this, output in your log file, for example, you should generally be increasing workmem. Maybe you should increase workmem for, on a per query basis or maybe on a per role basis, right? Like be a bit careful there not to overdo it. Because really what you're trading off here is if you go too high, you will hit out of memory, right? So if you have too much out of memory errors, really what you should be doing is reduce workmem to avoid them. Now, second, I want to talk about vacuum briefly. So vacuum in Postgres, right? Really important key operation, cleans up, data after you're doing an update or delete. Now, there are some basic things we can look at with vacuum, right? We can look at pgstat activity to see which vacuums are running right now. We can look at pgstat progress vacuum, which is new since Postgres 10 and is really useful to kind of know which phase this vacuum is in right now. But then really, I think the key recommendation, and this is actually what we applied earlier in this talk, is we need to reduce the cost delay in most cases. So before Postgres 12, the cost delay in Postgres was set to 20 milliseconds, which means that the maximum speed that a vacuum can run at is 8 megabytes per second. That's just kind of, how the math works out if you calculate it, which means that if you have very large tables, you will see vacuums running for days and days. Like I've seen, like last week, I saw a vacuum run for 19 days. And let me tell you, it's not a good thing if a vacuum runs for 19 days. Like things, the tables get bloated, you run at risk of transactionally wraparound. Like it's just not a good thing. And so instead of, adding more capacity, which, wouldn't actually help in this case because the vacuum would still be slow, really what you need to do is change the cost delay setting. And again, change in Postgres 12 was changing it to 2 milliseconds. I think that is the right change to make. I think, on all systems, except for maybe very small ones, you should just make that change. And then I think the other thing that has really, really helped in my experience with resolving auto vacuum problems or vacuum problems is using table partitioning, right? Like there's a lot of workloads that can benefit from it, like time series workloads oftentimes, where you're just adding data to a table and then you're deleting the old data. And so if you don't use partitioning, what happens is you're kind of poking holes into the table, right? And so then you're filling the data in again, like at random places in the table, which means that auto vacuum has to do a lot of work. Your sequential scans are often, very expensive because you're like scanning a lot of unnecessary data. And so table partitioning like saves a lot of vacuum work, saves, improves performance. So if you can, you should always use table partitioning, especially for anything that's larger than a couple of gigabytes. All right. Third, I want to talk about checkpoints. So checkpoints are important because we kind of, they're very IO intensive events in Postgres. So when you look at kind of, your overall structure, right, we kind of have the buffer cache, which contains, the things that are currently in memory that Postgres, retains there that are either, cached for future reads or that are, writes that haven't reached disk yet. And so the checkpoint is really the point where, the data directory gets synchronized so that for sure that, there's a safe point. If there's a crash, the data directory is fully synced to disk. And so because of that, syncing to disk, it is an expensive operation. It is also the point where if you don't have frequent checkpoints, it will mean that if a server restarts, it will take longer to get back up because there's more time to go back to the previous checkpoint. The most important thing to look at here is the checkpoint log events. So you can do log checkpoints, enable on, and then you just see all the checkpoints that are happening. And really the main thing to optimize from a performance perspective is not having a checkpoint be a xlog-based checkpoint or wall-based checkpoint, but a time-based checkpoint. Now, a wall-based checkpoint happens if your wall files that need to be kept around until the checkpoint happens exceed the max wall size. So if they exceed the max wall size, then a checkpoint is forced, and then it has to happen pretty quickly because Postgres is trying to optimize for disk space usage. Versus if it's a time-based checkpoint, it actually happens spread out over time because it doesn't have to immediately do all the I/O. And so if you're seeing a lot of I/O spikes, oftentimes checkpoints can be one of the reasons. The other thing we can do in addition to logs is we can look at these statistics. So there's pgstat bgwriter, which is kind of a statistics table in Postgres. And we can use that to also find out, how long do the checkpoints how long is the time between checkpoints, and what is the percentage of timed checkpoints. And then again, generally the two levers that you have is the max wall size as well as the checkpoint timeout. So those are kind of the two things you can do to make sure that you have as many checkpoints as possible. And then you can use checkpoint completion target for the time checkpoints to decide how you want to have the I/O done, right? So for example, 0.1 would mean that a checkpoint would try to complete within 10% of the full interval length of a checkpoint, versus 0.9 would try to do it kind of, at like almost spread out completely. And this again also depends a bit on if you have a lot of time checkpoints, and 0.9 is probably the good thing. If you don't have a lot of time checkpoints, then if one happens, you probably want that to happen quickly. All right, and last but not least, since I'm excited about Postgres 13, so I kind of want to show you a little bit what Postgres 13 can do. So let's kind of go back to what we had earlier, and let me switch right here. All right, and this, by the way, is still running on our little Raspberry Pi cluster here. And so here we can now do, let me connect again to psql, right? So we're kind of connecting again to our kind of local cluster here. So now I want to show you what we can do for wall monitoring. Let's look at statements. There we go. All right. So pgset statements generally shows you which statements have run on your system, right? So historically kind of gives you information about aggregate query statistics. And as of Postgres 14, it has gotten a few new kind of nifty columns that I like. First of all, it tells you about planning time now. We won't talk about that today, but just to call it out, it's a very, very cool feature. The other thing is it now tells us about wall records being generated. And this shows up in a few other places, by the way. And explain, for example, as well, you can now see how many wall records get generated by an update statement. So we were doing this insert statement earlier. So I wanted to take a look at how does that, kind of look from a wall perspective, right? And so we did 134 calls. I did a few before. We just did one when we were testing. And so now we can see, right, so there were 134 calls, and there were also 134 wall records generated by that, right? So each insert essentially caused one wall record to be created. We can also see how many bytes the wall kind of, bytes of wall got generated. And this is helpful because if we look at our system across, right, like everything, we could, for example, now say, let's see if this works. So we could now say, what was the most expensive thing to do on the system for kind of, in terms of wall records. And we can actually see, there was a temporary table create earlier. There was a truncate that was running earlier, right? So these were all things that, kind of ran earlier that had a lot of impact on the wall stream, right? And essentially caused a lot of wall to be generated. And this is, important for us to know, because then we can say, if we're trying to optimize our write workload, right, we're trying to optimize how many writes we're making, we can optimize for the things that are writing a lot of wall, because oftentimes that is what's causing issues, right? Like if read replicas fall behind, it is because a lot of wall is being generated, and so on. All right, so that is that in terms of looking at Postgres 13 wall monitoring. Let's switch back to here. All right, let's talk about sharding. So for sharding, sharding is really about scaling beyond the single server. So oftentimes, we keep adding our data, right? We follow best practices, we optimize our vacuum, we use partitioning, but there's still too much data, right? We're still kind of reaching, terabytes of data, or we're having performance issues that we're paying our cloud providers absurd amounts of money for provisioned IOPS, and it's still not working as we like. And so that's really where sharding comes in, is that it allows you, instead of keep adding on a single server, it helps you to scale out to more than one server. Now, there's different ways of doing sharding. Today we'll just look at one, which is we'll look at the Citus extension for sharding. So Citus is an open source extension for Postgres. You could, on your own system or on my Raspberry Pis, I could go right now and just, install it there and use it to scale out Postgres. So it's, like very, I would say, easy to get started, right? And again, it's tries to be something that is, straightforward to use as well, I would say. I would say the key feature here, right, is that we can shard the data across multiple nodes so that when a query comes in, like for example, you're selecting something from a particular table, and that comes into what's called the coordinator node. The coordinator node is kind of a regular Postgres server in the Citus terminology, that then kind of has the role of forwarding the query to the actual data nodes that actually run the statements. And so here we can see, we're selecting from one table, but really behind the scenes, there could be many tables, right? It could be 32 or 64 or hundreds of tables that get, queried in order to fulfill that query. And to the application, that means the application can keep doing its queries as if it was a single server, but, behind the scenes, essentially there's this kind of scale out architecture. And so as our last step here, let's take a look at how that works, right? Let's take a look at how we could actually shard in practice and how Citus kind of works under the hood. Now for this, we're gonna take a look at, so first of all, hyperscale Citus is what we usually call the service, right? Like we're kind of offering Citus not just as the extension, but really as a kind of, managed solution. And then we're gonna look at it in Kubernetes. And we're gonna utilize what's called Azure Arc. So Azure Arc is essentially the mechanism where Azure Data Services and other services from Azure are brought to environments that are not necessarily in Azure, right? So we could be running this on AWS or Google, or we could be running this on our own on-premise data center. And we kind of use the Azure technology outside of the Azure environment. So now I'll switch over to here, and it's the same terminal we used earlier. And so now we will connect to our VM here. All right, perfect. So this is a regular Ubuntu VM. This one actually runs in the cloud, has a bit more capacity than the Raspberry Pis. And so on this one here, we'll now, let me see, we'll first call AZ data login. So AZ data is kind of the CLI that we use for kind of connecting to Azure Arc. So Azure Arc, is kind of similar to the Azure CLI. This is kind of, what we use to communicate with the local controller. And so this could be, something that this could be something as you could be running if you were offline as well, right? So there are scenarios where you find yourself on a cruise ship. I mean, probably not these days, but you could find yourself on a cruise ship, right? And you still had kind of a Kubernetes cluster running hyperscale Citus using Azure Arc, and it could be managed locally through this AZ data CLI. Now, let's see what we can do here. So we can do Postgres server list. And so this is just going to list our kind of Postgres instances that are managed by this Azure Arc data controller on this Kubernetes environment, right? And so we have one kind of server group, what's called right now. So server group is, multiple servers or multiple pods. Can actually, look at that through kubectl. And so actually do this for all. So we can see here, right, like in our default namespace, like there's a few other things running as kind of main management tasks. But really the key thing that I want to show here is that, we have kind of 5 pods running Kubernetes. And so these correspond to kind of, the coordinator node and then the individual worker data nodes. And so if I wanted to connect to this, I'll specify kind of, the name that I want to access. And so then in a moment, there we go. So now, I can connect to this through here. And so now we can see here, right, like in this Postgres kind of deployment, we have our Citus extension, right, which gives us the scale capabilities. Now, actually drop this table for now. Let's do a new table. So I will kind of do an e-commerce example here. So I'll do just, really quick, I have my, let's call it, products, right? And so each product is kind of in a store. And then, that product has data associated, and we're kind of using a JSON-B column in Postgres. So now we're creating a regular table here, right? So now I could insert into this table, right? So I could do insert into products, values 1, 2, 3, and then I could, say something like, SKU And then this could be, well, let's say Apple, right? And so now if I did a select star from test, from products, I can see that, I kind of inserted that in there, right? Now, if right now, I'm actually not using Citus yet, right? So right now I'm just using regular Postgres. And so if I do an explain on it, I can actually see that this is doing just a standard sequential scan on this table. Now, what we're going to do is, we're kind of going to distribute this data. So we'll call create distributed table. We'll kind of, tell the product. And so then the other thing we need to do when we're distributing a table, we need to choose what to distribute the table by, right? Because we're not actually copying the same data on all kind of the data nodes. We're actually, splitting it up so that, some of the data is in node 1, some of the data is in node 2, and so on. And so here we're kind of choosing the store ID, as that kind of shard key or partition key. And so now if I rerun my explain, I can actually see that, the query is no longer just using a single node, but behind the scenes, it's actually, splitting it up into these different nodes. But, if I wanted to, I could, still query it as regular, right? Like no change necessary. So for the application, it, keeps being the same. Now, last but not least, I want to show you how this, kind of works for scaling out. So right now we have 4 data nodes here. Let's see if we can increase this to 6. And so, this is like, what's nice about this is instead of, like changing the size of your hardware, right? So if you went from, a single server that has, 4 cores to a single server that has 8 cores, that's usually an operation that takes time. Like it's very expensive sometimes, right? Because you always have to double the capacity. And so here, the nice thing is we could actually go node by node, right? We can just like scale out as if you're just like increasing capacity on a slider. And so if I go back to my, Kubernetes pods, I can see now, right? There are the 4 pods that have been running for a longer time. And then there's the 2 pods here that just, kind of came up just now. And whilst this was happening, right, my application was fully online. So I could have, kept running queries here. And then, as it's scaling out, these queries keep working. So there's no downtime, no impact to the application as you're scaling out. All right. And that's it, really. We took a look at quite a few things today. We looked at automation and kind of looked at how we can use Terraform, as well as how we can use PG auto failover to kind of automate your Postgres setups so that you don't have to manually do things. We looked at kind of some important tunings in Postgres, as well as what's new in Postgres 13, which I'm again very excited about myself, and I would encourage everybody to test. The beta just came out 2 weeks ago, so this is the right time to help the community test. Don't run production on Postgres 13. And then last but not least, we looked at kind of scaling out capabilities using the Citus extension. All right, and with that, I'm happy to hear any questions. All right, perfect. Thanks, everybody. So I think this is working, if I see this correctly. All right, so I'll essentially go through the questions here. If you have any other questions that have come up, especially in the last section, I know we have a bunch of questions on the PG auto failover sections initially, but if you have any questions on sharding, feel free to add them, and I'll get to them at the end. All right, let's see. So to start with, the first question we have here is asking, how is PG auto failover different from Patroni? If you're using Patroni, do you see a need for PG auto failover? And so I would say if you already have Patroni set up, Patroni is great, you should use it. So really the reason that we started PG auto failover like 2 years ago was that we felt Patroni was too complicated to set up, and Patroni required, not just standard Postgres components, but required additional changes. And so what we did with kind of PG auto failover is, build a standard, straightforward kind of Postgres, just a bunch of C code essentially with an extension Postgres as well, to kind of make it straightforward, right? So both Patroni and PG autofill solve the same problem, and I'm a big fan of what the team there has done. So it really comes down to what you think makes sense in your environment. All right. Next question from Shamik Banerjee. In the failover scenario, can we maintain one VIP to connect to the database instance so the app does not have to change connections during the event of a failover? So in the event of a failover, right, like when there's actually a problem, like when one of the instances is down. So what I was showing, and maybe this was a bit hard to see in the terminal, unfortunately, is that the connection string always has both host names, right? So you essentially don't specify one or the other, like you don't specify the primary and not secondary. You always have both present, and the client makes the decision which to connect to. Which again is a very, like, I would say, somewhat recent Postgres feature. So you need a client that I think is at least Postgres 10. But really the benefit of that is that the client can choose which one of the two is working and connect to that one. So you don't need any virtual IP. You don't need, kind of to change any connection strings. It just keeps working with the same string. All right. Next question from Patrick Rebrook. What happens if the monitor node goes down? So in this setup, we essentially protect against the failure of any one of the nodes, right? So we have kind of the primary, we have the secondary, we have the monitor. And so the idea behind the setup is that if the monitor goes down, your database is still online, right? And you're still replicating. However, automated failover would no longer be working. So it's kind of, a trade-off here where, and we could, and eventually, PG autofailover will have an additional kind of monitor node as a feature if you need that, right? But really what we're saying here is it's likely, like in most cases, a single VM will go down, right? And we're protecting against that problem. And I apologize for the background noise. There's a bunch of construction going on right outside. From next question from Remy Kura, about using 2 DBs and a parameter to connect with PostgreSQL. Unfortunately, I didn't see the full question there, so I'm not sure. I suspect isn't the kind of thing to maybe the follow-up was the next question there. Isn't it the kind of thing to do with a connection pooler? So I would say a connection pooler could also be utilized for that, right? So you could essentially have a connection pooler handle the same kind of connecting to either one of the two servers. Here we're essentially moving that all the way to the client. All right. A question from Brian Berryhill. Do you know of a published list of database parameters that cannot be changed when using an Azure Postgres service versus a VM? That's a great question. So today there isn't really a published list outside of what's in the Azure portal. So if you want to know, which parameters can be changed, just go into the Azure portal. There has been a lot of improvements there recently. So I would encourage you to, if you had issues in the past with changing a parameter, I would encourage you to go back and check again. I know the team is working hard on making as many parameters available as possible. It is always a trade-off. If you provide a managed service, it's a trade-off between allowing everything to be changed while still providing an SLA essentially. And so rest assured that we're trying to improve on this. But if there's any particular parameters that you see issues with, feel free to send me a message and I'll get it to the right folks. All right. Let's see. Next question from Ramesh Viswanathan. Create database hangs after creating the cluster using pgauto-ctl. So that sounds like a very particular question. I assume you tried pgauto failover and there was some problems there. So if create database hangs, it sounds like there was a problem with synchronized replication, which generally shouldn't happen, right? So generally what should happen is when the secondary is not available, it should switch to kind of async mode, or should actually switch to single mode, so that the primary does not wait on secondary. Now, if it hangs, it probably means that it does wait for a secondary. I would encourage you to open a GitHub issue. Again, it's an open source project, and I know the team, Dimitri in particular on the team here, is quite interested to find these bugs and fix them. All right, let's see. John Lovato is asking, so for applications to automatically fail over, they need to have both hosts and connection string. Yes, that's correct. So with PG auto failover, the design again is intentionally that the connection itself has both hosts available at all times, and that the connection itself, when it like with the target session attributes, what you're saying is I need a connection that's writable, and so it will connect to both. And if both are online, but one of them is only readable, right, because it's the secondary, then it will not use that. It will use the one that's writable. All right. Jan Lentfer is asking, does PG autofailover support multiple secondaries and sync replication? So today it does not. It is something the folks are working on. There's actually a pull request right now on GitHub that I believe Murat on the team is working on. If that's something, I would encourage you to subscribe to that pull request if you're interested. It's definitely something that's on the roadmap. All right, next question from Nivas, asking, monitor component in PG autofailover. Does it prevent split brain situation? Is it similar to Zookeeper and etcd? That's exactly right. So the idea behind the kind of the monitor component is that we do not need something like superbit etcd, right? So that's how Petroni, for example, solves it, is by having another kind of authoritative source that can say for sure that if you have a network partition, you know which node is actually primary, so you don't have two nodes believing they're primary. And so with the monitor component in PG Autofailover, we're essentially using a standard Postgres instance to serve that same benefit, right? So you're kind of reducing the number of different types of components you have to run, right? So you don't have to run a zookeeper or etcd, you just run a monitor, and that can avoid the split brain. All right, bunch of questions here. That's good. Let's see. Next question from Remy Kura. Do you think Workman could be set automatically after auto analysis of the hardware? So that's a good question. So I think I wouldn't. So Workman, I would say Workman is more related to your workload than it is necessarily about the hardware, right? So Workman really says how much memory can a query use when it's running, right? And if it exceeds the workmem, then it will spill to disk. And so there's a trade-off here, and I tried to allude to that briefly, which is either you run out of memory or you have things run slow because they spill to disk, right? And there's a sweet spot in between. And so I think ultimately what you need to do this automatically, which is a bit difficult, but ultimately you need to look at the temporary file log events to understand when do things spill to disk, right? In that case, you would increase workmem. If you run out of memory, you're running close to the memory limit, then you would want to reduce your workmem so that queries do spill to disk and use less memory. So it's kind of, it requires a bit of tweaking. I think in reality, what I've seen is unless you run a lot of active connections, it's usually not as much of an issue, right? So really, you don't want to run the default because that spills to disk a lot, the default being 4 megabytes. It's just too small for most workloads. But you probably shouldn't set it to hundreds of megabytes either. All right, next question from Sean McBarnard. Is there a concept of huge pages as an oracle? So I'm not familiar with the huge pages in Oracle. If they are the same concept as the huge pages in Linux, like the standard huge pages, then yes, Postgres can make use of that. There is a separate setting for that you need to turn on. There's a question here if you want to use transparent huge pages or if you want to use kind of pre-provisioned, like pre-created huge pages. I think these days transparent huge pages are somewhat safe to use. They're not as performant though as pre-creating huge pages. But if you search for Postgres and huge pages, you just find a bunch of documentation that talks about this. All right, next question from Remy Kura. Could you give hints about automating table partitioning? That's a great question. So I think it depends a bit on how you want to go about it. I would search again. There's many different tools here. I know pgpartman has been popular for many years now. You could also use Citus Data also create an extension called pgcron, which you could also use to do some of the automation here. But yeah, I think pgpartman is a good starting point for automation. All right, question from Brian Berryhill. Do you have a guide posted on getting Postgres 13 up and running on a Raspberry Pi? Yeah, it's a good question. I'm still very happy to have gotten the Raspberry Pi demo to work. I think it's actually pretty straightforward. If you just want to run standard Postgres 13, the beta has packages, so you can just search for, like, if you're using Debian or Ubuntu, just search for apt packages or like the apt package repository of Postgres, and there is a separate kind of URL that you use for the beta one, and so just specify that, and then you can use it on Raspberry Pi, assuming that you're running on 64 bits, which I would recommend. But yeah, like modern Raspberry Pi, it's just straightforward, nothing else to do. If you want to try out PG Autofailover, that is not packaged yet. There is a pull request that I actually created as part of creating this talk that fixes Postgres 13 support. So if you want to try it out, take a look at the GitHub. All right, let me see. So Mike Sanders is asking, are there any limitations like query complexity in using a shard manager like Citus versus more old school manual shard management based on partition keys and individual DBs? That's a good question. So let me think through that. So let's just look at yeah, so I think so generally I've not seen an issue with query complexity. I think the thing to know about, right, is so Citus is actually pretty good these days about handling complicated SQL. Now, the thing you want to be sure of is, what are you asking the distributed database to do, right? So if essentially when you're using something like Citus, always remember that if the data is actually split up between multiple worker nodes, right, that means that the full data set does not live in a single location. If you're doing certain kinds of things that, are, for example, not going onto partition column, but they're, going across different partitions, then you might be pulling data into either the coordinator node in Citus or like between the worker nodes. And so that might be something you want to avoid from a performance perspective. The good thing is you could just use explain to, look at that. But that's the one thing I would call out, I think, is it's less like complexity, like it's not a support problem necessarily, it's more performance consideration, like the way you data model your the way you select a shard key in your data model does affect performance, especially in a distributed setup. All right, Nivas is asking, for Postgres sharding solutions, how is app connection routing handled through a lookup table? So that's really, I think, the key benefit that Citus provides versus something, because you could always use this, do sharding in your application, right? You could just have your application connect to different database servers. And so the nice thing about Citus is that it's completely transparent, right? So if you have the Citus extension installed, it essentially hooks into Postgres. And so when you run a query, it will, like, let's say the store example from earlier, right? I run select star from stores or products where store ID equals 5. And then inside Postgres, there's a mapping from that store ID 5 to the shard, or the hash of that number 5, that then maps to a particular shard behind the scenes on a particular node. And so that happens without the application needing to do any lookups. It just happens automatically. All right, Lawrence Leahy is asking, can you use pgbouncer with pg-autofailover? That's a good question. So yes, you could use it. Now, I think the thing that might get tricky is the exact setup there. So if you're doing that, I would encourage you to, again, look in the GitHub. I know that folks are doing it. I don't know it right off. Dimitri on the team, I think, could share more on how exactly to use pgbouncer, especially with the kind of, multiple host names and kind of having that set up correctly. All right, Andrea and Florea is asking, any details about how Multimaster application geo-distributed works with hyperscale? Is this even supported? Yeah, that's a good question. So I would say Multimaster application is really a parallel problem to sharding, right? So sharding helps you in a sense that you can now scale out, and you could run multiple coordinators, which gives you a sort of active kind of setup. But I would really think of this distinctly from trying to solve something like Multimaster. So I would say, look at Citus, right? Let's see if that mix is a good fit. I know there's, BDR from Second Portland, for example, right? There's other solutions to do active, which are, maybe more suitable if you have a small workload that you need to replicate in a lot of places and you need to write in all places. When you consider any active kind of solution, I would always recommend you to really understand the trade-offs, right? So there is a reason that this is a hard problem, and this really comes down to, network latencies. So if, essentially, don't assume that if you, for example, use BDR, right, it will have its trade-off. It will have things that don't work as expected because, again, there's physical limitations. But I would say Citus itself is more really focused on that scaling out both the reads and the writes. All right, Venkat Kaushik is asking, what happens for an unplanned failover when the setup is more complicated? Like one primary, 2 replicas, DC1, DC2, and witnesses in a third DC. Does PG autofailover handle autofailover and rejoin? And how does it handle Stonex to prevent split brain? Yeah, that's a good question. I think it gets a bit complicated here, but ultimately I would say, right, so like 2 replicas, to your point, so that's not supported today. Once it is supported, I think this will maybe be handled a bit better. I think ultimately we should probably have this conversation offline. So feel free to either send me an email. It's lucas@fiddle.com, or open a GitHub issue on this, and then we can discuss this in more detail. All right. Ezilian Olanganathan is asking, what happens when we join 2 tables, one partitioned, another non-partitioned? Yeah, that's a great question. So this, in a Citus setup, right, coming back to this earlier notion of, some data might be in a worker node and, some data might be somewhere else. So in most of these use cases, there's a special table type called reference table. And a reference table in Citus gets replicated to all the worker nodes the same way. So that's, useful. Let's say we have, our stores again, and we have, maybe the stores themselves are a reference table, right? So the products are sharded by the store, but we want the full list of stores in all locations. Or maybe we want, let's say counties or something, right? Some kind of data that needs to be in all kind of locations. And so, this is kind of, the best thing to use there. All right, I think we're out of time. I think there were a couple more questions. I'll, try to get them later. Also, feel free to send me an email or reach me on Twitter. Cool. Thanks, everybody.